All right, I think I've got this. So what we're going to do here is we're looking at you on a wheel, one of these guys, where you're chugging along on your wheel and you see a saber-toothed tiger cub in the road. Probably has stripes because it's a saber-toothed tiger cub. Although they changed the name, so I think they call them saber-toothed cats now. Maybe they call them long-toothed cats because sabers are weapons and they're scary. So, but I remember them as saber-toothed tigers. That's much more nice. That's much nicer than saber-toothed cats because that makes the saber-toothed cats sound like they're soft and fluffy, and you might want to keep one at home. But really, most people don't want to keep a tiger at home, and I think that's probably true. If you found a saber-toothed cat, you probably shouldn't take it home, right? Sort of like Siegfried and Roy. That was a mistake. That was a big mistake. The big tigers. All right, so let's see what's going on. There's a tiger. It's in your road. Um, so you need to stop because you're moving here at 5 meters per second, cruising along on your sports model wheel, and you see this tiger cub in the road. It's 20 meters from you. You don't want to run over the saber-toothed cat because that would be mean, so you have to stop. So you stop, and you stop just in time. So the question is how much work do you do in that case? And I see another mistake. Oh well. So how are we going to do that? Well, we're going to use the work kinetic energy theorem again. Remember, the work is equal to the change in the kinetic energy. And one other thing the work is equal to is tau times theta, where theta is the amount of angle you need to apply the torque with. Now, we'll talk about that in just a second. Then the kinetic energy change is going to be reducing from the translational kinetic energy, which is 1/2 mv squared, plus the rotational kinetic energy, which is 1/2 I omega squared. But we're looking for this guy here, but we have these other three things, omega I, or theta I and omega. We have to figure out what each one of those things are because we don't have that data with us. Now, theta is probably the easiest, right? So what we mean by theta is the amount of angle this thing takes as it's rolling along here. So it goes several turns around there as it's stopping. So you want to find out the total angle that it's stopping at. So let's say one turn is 360 degrees, two turns is 720 degrees, right? So we're looking for something on that line. So it's 720 degrees for two turns. That's not how many turns we're going to do. We're going to do more than that. And we're going to only look at the radians, the 4 pi for 720 degrees. But I'm not going to bother converting that. But that's what we're looking at, is we're looking at that total angle that it's gone, not an angle between 0 and 360 degrees. So that total angle is going to have to be the total distance, which is 20 meters, over that radius, which is 1/2. So that's going to be 40. And we'll call that radians just to make you happy. Usually I just leave a number like that as a number. But that's in radians, so you can calculate that in degrees if you want. You can calculate that in rotations if you want. And I'm sure you'll have a great time. So we did this guy. Now we need the other two. We need the moment of inertia and the angular speed. The moment of inertia for a solid wheel. Remember last time we did a hollow tire. Now we've got a solid wheel, so that's 1/2 mr squared, whereas last time it was just mr squared. And that's because the farther out you go, the farther out you go, a mass element has a greater moment of inertia. And in that case, because we we're pretending that the tire was an open cylinder, all of the mass was at the edge of the cylinder, so it had a really high moment of inertia. This has a lower moment of inertia because it's uniformly distributed. Or at least we're pretending that it's uniformly distributed, and we're not looking for inhomogeneities in the rock. Okay, so that's 50 kilograms for that guy, and the radius is 1/2 meter squared. Shouldn't have put that guy in there, oh well. So that's 50 divided by 2, divided by 2, divided by 2. So 50 divided by 8, and that's 6.25 kilogram meters squared. So that's the moment of inertia. And finally, we have to find the rotational speed that we started at. So this is our initial velocity, which we know that's 2 meters per second, or 5 meters per second, excuse me. 2 meters per second was the last one, the last video. Radius is 1/2 meters. Okay, so with 5 meters per second divided by 1/2, that's like 2 times 5, so that means omega is going to be equal to 10 inverse seconds. So we've got all of the things we need to go on. All right, so now all we have to do is plug all those numbers in, right? I thought I looked at this and it had the right answer on it. Uh-oh. Because this is not the thing that I see. So we have to add in the 1/2 mv squared. All right. So that's another mistake. Let's see. We need t times theta, tau times theta. Theta is 40 radians. So that's tau, what we're looking for, times 40 is equal to 1/2 I omega squared. That's 1/2 times 6.25 kilogram meters squared times 10 hertz, this thing, 10 inverse seconds squared, plus 1/2 times the mass, which is 50 kilograms, okay, times the speed, which is 5 meters per second squared. All right, so calculate the first one. That's 625. 100. 10 squared is 100, so 6.25 times 100 is 625 divided by 2, so that's 312.5 Newton meters, plus, let's see, 1/2 times 50, that's 25, times 5 squared, which is 25, so 25 times 25 is 625. They look very similar, Newton meters. And so that is going to be equal to what? 937.5 Newton meters. Okay, so now we have to divide by 40 to get the tau, the torque, which is what we want to figure out is how much torque we applied. All right, so that's 9, so that's like 2. So we have 13, 137, so that's 3. 3 and 40 is 120. That's 17 left. It's 170, so that should be another one, so 4, I think, Newton meters. You might check that out. Maybe it's 23.5 Newton meters is the amount of torque you need to stop this. And here's the other mistake, plus. Okay, so that's about it. What we looked at here is when we're using this definition, we have to find the amount of angle that you traveled over, or that, a point on the wheel traveled over the distance, 20 meters, over the distance over the stop. So we need to find that, in radians. Okay, you can't find it in degrees. You can't find it in any other sort of system that you want to look at it. In rotations, it doesn't work. It has to be in radians, and that's the same as this guy over here. So we had to find that theta, but other than that, the idea is the same. Tau times theta, torque times angular change, that is similar to, not equal to, the force times the distance. So just for rotational motion. Then mv squared is the same thing we've been using, right? So we don't have to worry too much about that. And I omega squared is dependent on this moment of inertia, and that moment of inertia you have to calculate over there, but that's the rotational kinetic energy. That's the rotational part, and that's the linear part. You multiply it all out, it comes together, and you get a nice looking number, which is 23.4 Newton meters, which you probably can do, so you're probably okay. So you should check that out and see if a wheel is the right thing, the right mode of conveyance for you. All right. By now, I will talk to you soon.